Hi, my name is Jessica Shi, and I'll be presenting our work on scalable community detection via parallel correlation clustering. And this is joint work with Lakshman Dhulipala, David Eisenstadt, Kuba Laki, and Fahad Mirakni, all from Google. So to begin with, graph clustering is a fundamental problem in modern data mining with applications in multiple areas, including social networks, where it can be used to find communities of people under various criteria. It's also used in bioinformatics. So here is an example of a protein-protein interaction graph, where clusters of interacting genes suggest risk factors for autism. And it can be used in machine learning pipelines, such as in facial recognition, where this is a facial similarity graph, and clustering can divide faces, in this instance, based on age. Now, parallelism enables us to efficiently process large graphs. For the purposes of this work, we'll be focusing on shared memory parallelism, and we'll be processing graphs with up to billions of edges. So the main goal is to develop a scalable graph clustering framework with high quality and ground truth data. And in order to do this, we focus on the Lambda CC objective. This was first developed by VLDB et al. In 2018. And this is a generalized objective that unifies several quality measures. It's a generalization of the widely used modularity objective, and it interpolates between the sparses cut objective and the cluster deletion problem by use of a resolution parameter. So in a bit more detail, for edge weights wij, which are 0 if there is no edge between any two vertices, and node weights ki, which are initially 1, and a resolution parameter between 0 and 1, we would like to maximize the sum over all pairs of vertices in the same cluster of the edge weight minus the resolution times the node weights. And essentially, the basic idea here is to maximize agreements within a cluster. So our main result is a highly optimized correlation clustering implementation called PAR-CC. We developed tunable optimizations, and we performed a comprehensive evaluation that showed their performance and quality improvements. And we also show up to 28.44x speedups over sequential baselines on a 30-core machine with two-way hyperthreading. And we also show high precision and recall compared to ground truth clusters with trade-offs depending on the resolution parameter. Now, we compared our work to state-of-the-art clustering implementations, and we show that we can obtain significantly better objective compared to the pivot-based correlation clustering implementation C4 and ClusterWild. And the special case of the modularity objective, we show up to a 3.5x speedup over the state-of-the-art parallel modularity clustering implementation NetworkIt. And finally, we show high precision recall compared to ground truth, and we show that we outperform the triangle-based clustering Tectonic. So now we'll go into a bit more detail about our algorithm. So to begin with, it's NP hard to optimize for the Lambda CC objective. So we actually use the Louvain method, which is a well-studied heuristic. And essentially the way that this method works is we first move each vertex to its best cluster, optimizing for the Lambda CC objective and considering all vertices in a fixed random order. And then we repeat until no vertex moves are made. And then once we're done with this subroutine, we compress the graph such that every cluster corresponds to a new vertex. And then we repeat this entire process until we reach a stable state and no vertex moves are made. Now, there's a bottleneck in parallelizing this method, and that's sequential dependencies and moving vertices to the best cluster. So for example, in this graph here, where you have vertices A, B, and C, we see that vertex B and C would each like to cluster with vertex A, but they would not like to cluster with each other because there's this large negative edge here. So now if vertex B clusters with vertex A, then C's best move is not to cluster with vertex A and vice versa. So there's a sequential dependency. Now our solution to this is to just relax the sequential dependency and allow vertices to move concurrently. So we have no convergence guarantee, and we use a constant cutoff in terms of the number of iterations in which we run the best vertex move subroutine. All right, so now I'll talk about some of the practical optimizations that we considered. The first optimization is in performing the best vertex moves. So in the algorithm we've just presented, we use the synchronous setting where we compute the desired cluster of each vertex in parallel, and then we move all vertices to their chosen clusters in parallel. So in this example here, we see that vertex A chooses to cluster with vertex B, and vertices B and C would each like to cluster with vertex A. So if we perform some symmetry breaking, we see that we have one giant cluster when we move all vertices to their chosen cluster. And this contains vertices A, B, and C, except this actually has a negative Lambda CC objective of -1 if we take the resolution parameter to be 0. And this is because B and C have a large negative edge weight between them. So to improve this, we consider an asynchronous setting where we compute the desired cluster of each vertex and then immediately move that vertex to its chosen cluster. And this relaxes consistency guarantees. So in this case here, perhaps vertex A and vertex B compute their best moves before vertex C has a chance to compute its best move. And then they move and they cluster with each other before vertex C computes its best move. So then by the time that vertex C computes its best move, it sees that it would no longer like to cluster with vertex A and B. And now we have a positive objective value in this clustering. So in practice, we see up to 2.5x speedups using the asynchronous setting over the synchronous setting. And we see up to 156% increase in objective using the asynchronous setting over the synchronous setting. And this is due to the symmetry breaking available in the asynchronous setting. So our next optimization is in the subset of vertices that we consider when we perform the best vertex move subroutine. So instead of considering all vertices, we can instead consider only vertices that are neighbors of previously moved vertices. So in this example here, if we have vertices A and B in a cluster and vertices C and D in a cluster, and now C changes its cluster to move with A and B, then the next round of best vertex moves, we consider only the vertices B and D, which are the neighbors of vertex C, and we don't consider vertex A. So we see up to 1.9x speedups using this optimization over all vertices, and we see no significant change in the objective obtained using this optimization. Now, the final optimization is multi-level refinement. Essentially, after the algorithm is finished and the last compressed graph is computed, we traverse back through the previous compressed graphs in order, and we repeat the best move subroutine on each previous compressed graph. And this is particularly helpful if the best move subroutine did not converge originally before graph compression occurred. And this can occur because of our sequential, because of our heuristic relaxation. So if we use this optimization, we see up to 2.29x slowdowns using multi-level refinement because it's an added step, but we see up to 36.90% increase in objective. So the best optimizations in conjunction with each other are the asynchronous setting, considering neighbors of vertices, and considering multi-level refinement. And we see up to a 5.85x speedup using these optimizations and up to a 156% increase in objective using these optimizations. So now we'll go over some of our experiments in a bit more detail. So our environments are a 30-core GCP instance with two-way hyperthreading, and for large graphs with billions of edges, a 48-core GCP instance with two-way hyperthreading. And we consider graphs with ground truth communities. So we consider unrated real-world snap graphs with up to 1.8 billion edges, and smaller weighted graphs from computing the KNN on real-world point sets from the UCI machine learning repository. So these two graphs show our speedups over our sequential baselines of our parallel implementations for correlation clustering on the left and modularity clustering on the right over a variety of graphs. Essentially, we see up to a 28x speedup, and the speedup changes depending on the number of rounds needed for convergence. And now in comparison to existing baselines, we see that the pivot-based correlation clustering implementations, C4 and ClusterWild, are up to 429x faster than our implementation, but they give up to a 433% decrease in objective compared to our implementation. So they have significantly worse objective. And in the special case of the modularity objective, our implementation is up to 3.5x faster than the state-of-the-art network GIT. And for triangle-based clustering, our implementation is up to 67.62x faster than the state-of-the-art tectonic. So these graphs show a comparison of our implementations to ground truth clusterings. So on the left, we show a comparison of our parallel implementations for correlation clustering and modularity clustering compared to the sequential baselines. Essentially, we see that we match the precision recall obtained by the sequential baselines pretty closely in both instances. And on the right here, we show the precision recall of our implementation compared to tectonic. And we see that we significantly outperform tectonic in terms of the precision recall that we're able to obtain. So in conclusion, I've presented our scalable graph clustering framework for RCC that has high quality on ground truth data. And I've shown improved performance and quality over the state-of-the-art clustering implementations. And our code is publicly available at this link here. Thank you for listening to my talk.